Okay, some students said they didn't know how to start question number 1 in the homework. Is that correct?
No, I just don't understand the reasoning behind the reason.
Yes. Okay, so let's look at this. Let's see, there's 2 sections to it. 2 points, point 1 and point 2. So you see the 2 points are located inside a region with an electric field pointing to the left as shown. If a proton is moved from point 1 to point 2, so I have a positive charge that goes from here to there. Will the potential energy of the charge field system change? And then how will it change? So the first question of will it change? What was our rule about when work is done? Work is done if you have a blank that is blank to the blank. A force parallel to the distance it moves. So in my picture, what direction will the force on a positive charge be?
Wait, parallel?
Work is force times distance parallel. So in my picture, what direction will the force be?
The left.
The force will be to the left because you have a positive charge. So the force vector is equal to Q times the E vector. So that means my force on that positive charge is like this. Okay, force vector is Q times electric field vector. That's the point of the electric field to allow us to find the force easily. So if we have the electric field is pointing to the left and we have a positive charge.
Pointing to the left is the arrows?
Yes, the words say it as well, but the arrows point left. And so on a positive charge, the force is going to be the same direction as the electric field as per the equation in red. So now, we have a force to the left. So since work is equal to force vector dot delta x, or force times distance parallel, or force parallel times distance, the question we have to ask ourselves is, did the charge move any in the left or right direction? Yes. Did it move to the right or to the left? It moved to the right. So my distance was to the right. Actually, I should go up here. To the right. But my force was to the left. So it moved the opposite direction as the force. So did that do positive work or negative work? It did negative work because they're opposite directions. So there was negative work done on the charge. And since change in potential energy is minus the work, because this asked about potential energy, right? So the final thing is, change in potential energy is defined as minus the work. Since the work is negative, then the change in potential energy is positive. So we're going to have the potential energy increases because the charge moves against the force. Now, using this as a learning moment, I drew a random path with my blue arrow there. What happens if the path changes? What happens if I make my path like this and like that?
No work is done on the first leg, and then work is done on the second.
Okay, no work is done on the first leg, and it is on the second. If you have a conservative force, the path doesn't matter. So you have the same change in potential energy regardless of which path you took. So if you're doing a calculation, which path do you choose? The one that has 0 on one and then it's parallel on the other. That's the easy way of doing it. So our answer for the first one, if the proton is moved from point 1 to point 2, the potential energy of the system will have to go up because you were, the field did negative work, so you had to do a positive work to move against the field. So that means you added energy to go against the field. And then we have number 2, if instead an electron is moved, Oh, if you change the sign of the electron, what did you change fundamentally in our problem?
The direction of the force.
The direction of the force, because you have a minus here, so the force is in the minus direction of the electric field if it's a negative charge. And so you just reversed your answers.
Can you explain more about how the potential changes and how that's different than the potential energy change?
I haven't talked about potential yet. So when I talk about potential, I will. But we haven't talked about potential yet, so I don't want to muddy the waters. Okay, now, for the sake of Maxwell, I, of course, completely missed 2, but I think this will get there. Yeah, problem 2. Consider 2 points in an electric field. The potential at point 1, V1, is 43 volts. The potential at point 2, V2, is 165. Protons move from point 1 to point 2. Write an equation for the change of potential energy. Okay, now this is something I thought I had been very careful not to have this problem. Whoops, change back to drawing tool. Change in potential energy is equal to Q delta V is our equation. There's your starting point. So you have Q given to you because it's a proton. If it's a proton, Q is equal to plus 1.602 times 10 minus 19 coulombs. And you're given V2 and V1. So delta V is V final minus V initial. And you just put those in. And that will come up. That's it. Oops. Change back to this just to make sure.
So what is the U representing?
U is an alternate symbol for PE.
Okay.
It's potential energy. Just like we in some levels of physics, we use T for kinetic energy, U for potential energy.
You said Q, right? Q delta V?
Change potential energy is Q delta V, yes. Yes, it's a proton. For a proton, that's always the case for a proton.
So you did that times.
Don't do anything with E.
I got that wrong.
Don't do anything with what?
If I put E in there, I got it wrong. So I just did B to the minus B1.
Oh, I see what you have down here. Yeah, you're doing an equation. I'm trying to erase and failing miserably. You're doing an equation, so it should be E times V2 minus V1.
No, it's
That's
just
the
V2 minus
equation
V1.
for part A, but then part B, if you put that number in for E. So that would be right. And then if you go to part B,
Going super, super fast. And then solve numerically, so you're just putting in the numbers. Okay, EV. Let me talk about EV later in the lecture. That's probably what you're getting confused about. So let's go to our lecture.
I'm confused because I thought, so maybe I've been doing it wrong the whole time, but does our homework not correlate with the lecture?
Oh, it absolutely does. I did not. I apparently didn't screen them carefully enough because I looked through and tried to make sure I didn't have anything with electron volts or with voltage.
Isn't that the same thing for one though? Like that we have one?
No, number one we absolutely had.
But even the second part, how will the potential change?
Did it say how will the potential change?
Mhm.
No, how will the
Yeah,
potential-
problems. That was the second part of part A. It
There was
literally
two
says,
parts.
how will the potential change? How?
Oh.
That's
Wow.
why she was asking.
Then I
about
did
it.
not do as well in screening the problems as I did. I thought I'd screened them all. Okay, so that's why she asked. I will cover these in the lecture today. But yes, this was supposed to be all stuff that I covered last lecture, and I apparently made a mistake here.
Okay, yeah. Let's just do that. C.
Okay, so let's go through the lecture, and hopefully those answers will be clear.
numbers, letters C.
That's okay. So just a review of what we've covered. On Wednesday, we talked about the electric field lines and how electric field lines are always going to go out of positive into negative, and they're vectors, and you can add those electric field lines up. They can never cross. If electric field lines are close, you have a stronger field. If they're far away, you have a weaker field. Then we ended with electric potential energy, which is all I thought I was asking you about in those questions. Today we're going to talk about electric potential and the electron volt, two things that you had in those problems. And so we're going to get on with that idea. This is the last slide we had last class period. I added the equations here to make sure it's really clear. These are graphs of how the potential energy, the first one is gravitational. Potential energy between two masses. The potential energy for gravity is minus g m1 m2 over r squared. So it's always negative. With what separation, if I have two charges of fixed mass, what separation is going to give you the minimum potential energy? For two masses.
The biggest distance.
Okay, if you put in the biggest distance, then you're dividing by infinity, and it's 0. But 0 is actually the maximum, because you have a minus sign. It's the smallest magnitude, but since it's all negative numbers, that's your maximum potential energy when they're infinitely far away. And so what's going to give you the minimum potential energy? Being as close as possible. Touching, right, would be infinite. So with mass falls down because things naturally go to lower potential energy if they're given an opportunity. That's why it falls down. It's going to lower potential energy. Now if we go to charges, the first picture, Q1 times Q2 is less than 0. So that's like exactly. One is a positive charge and one is a negative charge. So in that case, Q1 times Q2 is a negative value. And so we have K times a negative value divided by R. Looks exactly the same. So you have the same shape. So if I have a positive and negative charge, what separation is the lowest possible potential energy? As close as possible together. And the highest possible potential energy?
As far apart as possible.
Infinitely far apart when the potential energy is 0. So these equations, both of them, have a built-in reference point. 0 potential energy is when they're infinitely far apart. Now, if I have two charges that are the same sign, either both positive or both negative, then I have a positive in the numerator up here. And so then it reverses everything. So you have an infinite potential energy if they're right next to each other, and it goes to 0 if they're infinitely far away. And so those are always repulsive. They try to get to lower potential energy and so they try to move apart. Now, first problem of the day. My goal is always for me to do a problem within the first 15 minutes. And look, I made that goal today. In a thunderstorm, charge is separated through a complicated mechanism that is ultimately powered by the sun. Okay, so what's that mechanism? You have water falling through ice crystals. You have the rubbing of water on ice. Why is it ultimately driven by the sun? Well, over 99% of everything that happens on Earth is driven by the sun. The sun heats the air, causes hot air to rise, and that's ultimately the driver. Okay, so the simplified model is shown here where it just has one positive point charge. 50 coulombs. Is that a big or a small charge?
Sounds pretty big.
That's pretty big, right? Everything we've been doing is like in nanocoulombs or microcoulombs. That's a big charge. Separated by 8 kilometers. 8 kilometers is a pretty big distance too. Although I have to point 8 kilometers elevation. Yeah, that's pretty high. And then we have minus 20 coulombs down here. Is that going to make an electric field? Just looking at the line connecting the two, what direction would the electric field point? Because
there's a closer attraction between the ground and the bottom of the planet.
well, no, because it goes out of positive and into negative. Now, if we had drawn all the fields, since this is the bigger charge, it would have been asymmetric, something like this. For the electric fields, going other directions. But that's the direction the electric field is between them. That's not the point of this slide. But I want to make sure that we have, some understanding when you see lightning, hear thunder, have some understanding going on there. Yes?
Does it always go out of positive and it's negative?
Electric fields always go out of positive into negative. Andy?
Would it be entirely inappropriate to think of it as a source and a sink
Um,
of electrical field?
No, I never think about it in that way because when you say source of sink, I immediately think about electrons instead of electric field. But yeah, I would think that's okay. So here's why I have this. To do the problem, what's the potential energy of the pair of point charges? So what was that potential energy equation? We do have to go back to the first slide today. That is also, well, that's changing potential energy, but that is a correct equation, but we couldn't use it here because we don't have the delta V information. So if I do this, my K is 8.9876 times 10 to the 9th meter squared per coulomb squared. Then I have to multiply that by 50 coulombs and by minus 20 coulombs. And I divide the whole thing by 8 kilometers, which is 8,000 meters. So if you put that in your calculator, 50 times 20 is 1,000. So that's 8.9876 times 10 to the 12 divided by 8 times 10 to the third. It's basically 1.12 times 10 to the 9th. Yes, negative. Negative, thank you. I thought you were saying to the negative 9. I'm like, yeah. So, was that hard to do? No. I calculated the potential energy between those two charges. Because they're opposite charges, what would it like to do to minimize potential energy? Come together. How does it make that happen? By having electrons pass from the negative region to the positive region in a process we call lightning. So it's just trying to relieve that energy difference. What caused the energy? It was actually from gravitation, from the falling of the water in the ice, right? So it converted gravitational potential energy into electrical energy, and then that electrical energy caused the lightning strike, which converted energy into heat and sound. It's all very interesting, I think. And that's what nature is. It's interesting. Now, what if you have more than one charge? I had just or more than two charges. I had two charges, one pair. And to calculate the potential energy, it was straightforward. But what if I had three charges? Let us say that Jenna has a charge, and David has a charge, and Maxwell has a charge. And I want to find the potential energy in the set of three people. How do I do that? Well, the answer is up there. I just calculate the potential energy between these two, potential energy between those two, and the potential energy between those two. That is, I calculate each possible pair. And I add them up. Now, in this picture, when I said the potential energy was minus 1.12 times 10 to the 9th joules, what would you say that potential energy belongs to?
The distance between the two charges. Like the two charges themselves, not including the ground.
Okay, the two charges combined, the entire system. So when I go to the system that has more than two, it's once again the entire system. It's not energy just of Maxwell's, it's energy shared between all three of them. Okay, so you ready for your problem? Sure you are.
Mm-hmm. Just the one. Now it's on a straight line.
Okay, so here's a problem to work on. Find the electric potential energy for the array of charges, it's only three charges, shown in the figure, and gives you the value for each charge and the location for each charge. Do it.
I'm not going on the trip anymore.
Is that like R13, number 13?
Okay, so Max's question, R13, that's the separation between 1 and 3. Is how I chose. Actually, I didn't make this, but it's how the subscription chose. So the separation between 1 and 3, if you look at the values here,
Oh,
charge 3 is located at x equals 3, y equals 0, and charge 1 is located at 0, 0.
so that's 3.
So it's 3. Yeah. Actually, looking at the pictures quicker, figured that out than looking at the numbers. And to save you time, this is a 3, 4, 5 right triangle. That is 3 squared plus 4 squared equals
Yes,
yes.
they are meters.
Include is it the magnitude of the charge, or do you include plus and minus?
You include the signs.
Thank you.
That would be much better than my target of having you guys start a problem by 1/3.
Yeah. I don't know about that.
What's the rate?
I assume, let's see, we have 8 and minus 12 and minus 6. I didn't make sure that 8 went with the right number, but I assume you got that one pretty good.
I got like 3 bajillion. And I got like 505.
3 bajillion.
That's a technical term.
It's 3.505 times 10 minus something.
Just 1 to 2 there.
But negative.
This one's.
Technically, that's
This one should be 4,
3.5
and
bajillion.
Yeah.
This is 7, 8, 10. 3.505 times 10.
There we go. Sorry, what?
No, you guys got? Or did you get something different?
So
I never assume everything. I always think
right,
it is.
so it's like 1. There you go.
I'm just like, this is wrong. What have I done?
At least you want to be like, and then 1.
Oh, I
Copy when you get
didn't
around
think
it.
it's close. I did something else.
No.
Oh no.
That's gonna, instead of bajillion, it's gonna be 0.0.
Negative.
I'm still good.
It feels like breakfast today.
That's not what it looks like.
Okay, now I have negative 35.
Is that not doing a limit problem?
I'm trying to get it for chapter.
You only make my mistakes, so I'll compare my mistakes to your mistakes. It's nothing personal, just, I don't know what my answer is.
Email regarding the project is being viewed.
I mean, I just haven't had time, sir.
Okay, so Q
Yes.
is negative 12 over 2. Yeah.
I think I'm good.
What you got?
I got negative 0.0350.
Did I?
Ha
Wait, what did you get?
Negative 0.0350.
That is close-ish.
ha! Close-ish.
Negative 0.048. I guess now I got negative
Oh.
0.035.
I've noticed just filled in.
I got negative
1,
3,000.
1, 2, 1, 3, 2, 3.
Okay, so
Radiuses are.
turned out that wasn't too difficult, right?
I don't know why I'm getting writing this wrong.
I'm going to write this the way that Sarah Andy did, and that is potential energy is equal to K times, and just do the pairs, Q1, Q2 over R12 plus Q2, Q3 over R23 plus Q1, Q3 over R13. Factored out the K because everything's multiplied by it. And then if you multiply through, Q1 times Q2 is 8. And don't forget that's going to be 10 to the minus 6 times 10 to the minus 6, so times 10 to the minus 12 coulombs squared. And the separation between 1 and 2 is, and I got to make sure what my units are. They're meters, okay. 5 meters. And then I have for 2 and 3, 2 is 2, 3 is minus 3, so that's minus 6 times 10 to the minus 12 coulombs squared over, and between 2 and 3, that's 4 meters. And then finally, between 1 and 3, 4 times minus 3 is minus 12. Because the 2 times 3.
No, because what's happening is you have something times 10.
And then you just put it in the calculator to get your answer.
And when you multiply
Now, any questions about this process before we move on? Andy?
What was the answer again?
The answer is 0.035.
0.035.
And so why?
I'm taking that because you got that, he got that, she got that. I didn't do the calculation.
I forgot to convert to coulombs and then I fixed negative.
Yeah, well, the total overall answer is minus, yes. I'm sorry.
What did you say the answer was?
Minus
0.035.
Oh,
Yes.
yeah.
I get the right answer. Yeah. Okay.
I forgot to convert.
Whoops, only 2 sig figs.
It's like 500,000
Oh, yeah,
times
you're right.
greater than I needed.
Joules.
Always better to do it. It's fun.
Okay,
Yeah.
shall I move on?
I've done it right.
I like that for new taxes.
Now, electric potential. This is where we start talking about electric potential. Electric potential, I have it in words here. I have an equation form in the next slide. Electric potential is defined as the electric potential energy per unit charge. We've seen something like that because electric field was electric force per unit charge. So it's really fundamentally the same idea. That gives you the relationship that I wrote down for problem 2. Since electric potential energy, or electric potential, the symbol for electric potential is V. Then potential energy is Q times V. But here's a thing, an important thing. You might have noticed me waxing eloquent on this on slides on Perusall, that potential energy is always in reference to some location. Remember when we were talking about potential energy equation, I said it has a built-in reference for the point charges that infinitely far away is 0 potential energy. So this really is always delta V and delta potential energy. So anytime you talk about potential energy, it's always in respect to a reference point. Thus, anytime you talk about electric potential, it's in reference to some reference point. Now, in terms of units, the symbol for electric potential is V. And the unit for electric potential is V. Isn't life good? Both the symbol for it and the unit are V. And because the unit is called a volt, the electric potential we often simply call the voltage. So electric potential and voltage are identical in meaning. The textbook tries to draw some funny line between them, but there's none. They're the same thing. And they're always a difference. So sometimes we'll talk about the potential difference because it always is when you're measuring that. Now, in terms of units, if we look at this definition, the unit for potential energy is the joule. The unit for charge is the coulomb. So that means that my voltage has units of joules per coulomb. So we call that a volt. So 1 volt, see in the little box at the bottom, 1 volt is 1 joule per coulomb. So now we have reference for anything that has voltage. So we have 120 volts coming out of this. That means that we have a potential energy difference of 120 volts per coulomb. It's not what you think. We'll have to learn more about AC before that can make actual sense to what really is going on. But we at least can understand that's talking about how much energy the charge has. So you can see there's the equation written out. We have learned about the potential energy equation between 2 point charges. That's the equation that you just worked out in your problem. So if I have 2 point charges and I use this equation, then for a point charge, so I'll put PC to stand for point charge, the voltage is equal to K Q1 Q2 over R divided by Q2, right? Because we have to divide by one of the charges. The one that remains is the one that we have. Surprise. And so that's KQ over R. So the voltage caused by single point charge is KQ over R, where R is how far away you are. Something that caused great discussion on Perusall is this is a scalar value. Do you guys ever see my comments? Oh, you see it in the email. Nice.
We get an alert saying you reply or something.
Good to know.
I only see your comments on mine specifically because of the email thing, because there's so many comments that like I don't want to.
I can do that.
I feel like you only get emails about like if they answer to you.
If you're involved in the thread. That makes sense. And to try to keep the spam down as low as possible. So this is a scalar value, which is wonderful. I prefer scalars over vectors, every day of the week. Why? Because I can just add them. I don't have to worry about the directions. So electric potentials, i.e. voltages, simply add. So if we go back to the problem we did here, if we had asked for the voltage, now the voltage has to be at a location, right? We have the potential energy between those 3 charges. We'd have to say, what is the voltage? What is the electric potential at X location? And then we would just calculate what the voltage from each of those charges are, add them up, and would be done. So I just did this work. I can skip over that. Time to go to Woo Clap. Thank you. We're up to 7. 3 more. 8. 2 more.
I'm sorry.
Okay, everybody's in. Excellent. Here's our question. A point charge always naturally moves to a position of lower potential energy. What does this tell us about the natural motion compared to electric volt or potential? So what it's asking is, does charge move to higher or lower voltage? Remember, electric potential means voltage. Got our first answer. Seven answers now. Don't want to cause consternation, but of those 7 people, 1 person is correct. We have 8 now and 1's correct. The reason we do these is so we can rectify these thoughts and not have people leave with an incorrect understanding. Final 2. Okay, well, let me summarize the answers for the 80% who participated. 6, 0, 1, 1.
Oh, good Lord.
So 6 people know they were wrong.
Yeah.
So we started, everybody understands about things move to lower potential energy, right? And force is actually just a result of that. So if I have a negative charge, where does negative charge have higher energy? If it's close to positive or close to negative? Close to positive. Now electric field lines go out of positive, right? So electric fields are going to go opposite those electric field lines. Agreed?
Wait, what?
Okay.
No, I don't agree.
I don't agree. I don't agree at all because I don't know what you said.
I know what you said, but the way that I understood what you said sounded wrong.
Here's a positive charge, and here's an electron. The electric field lines for that positive charge are going to radiate outward like this. And remember, we had the potential energy, the electric potential for point charge is KQ over R. So that means if we go with the electric field, we're going away and the voltage is getting smaller. So this is high voltage. And this out here would be lower voltage. And so the electron is trying to get closer to that charge. Whoops, missed. Trying to get closer to that charge because it's attracted. So the electron goes that direction. So the electron goes toward higher voltage. Why? Because the potential energy is equal to QV, or let's put it with the deltas. And so since Q is negative, if delta V is positive, that's going to make delta PE negative. Right? If you have a negative Q, then to have a negative change in potential energy to go to lower potential energy, you have to go to higher voltage. But a proton, a positive charge, would do just the opposite. Because it has a positive Q, it's going to try to go to lower voltage, to go to lower potential energy. So both are going to lower potential energy. But that means that a negative charge goes toward higher voltage, whereas a positive charge goes toward lower voltage. And notice I switched between electric potential and voltage a lot. Voltage is the colloquial term. It's what we usually say. I'm trying to say electric potential as much as I can just to make sure we have that mesh that electric potential means voltage. Okay, so any questions about that? No? If I asked it again, you would all be able to answer correctly? And you would know the reason why? Okay. I don't know why. Just wanted me to feel good. And I've talked about everything that's on this slide because, hey, I've been thorough. So it's time for a second woo clap. An electron, I'm going to quote that. Whoever said that. Woo clap is enormously popular. Aaliyah loves it. An electron is placed between two plates. So I have two plates. One plate is at minus 10 volts. One is at plus 10 volts. And I have my electron midway between them, minus Q. And so the question is, in which direction will the electron move? Or will it?
Let's wait till the results.
Let's wait. There is good pedagogical reason for you to put in an answer beforehand, because if you're right, it helps you to affirm you were thinking about it right. And if you're wrong, then you recognize, like on the last question, whoops, I didn't understand what I thought I did. Because everything we do in class has some reason. I'm sorry, I got to start again. Okay, now you can answer, Max.
Are the answers in there correct so far?
Well, some of them are, some of them aren't.
Now is there one list?
That was the one less. I shouldn't have used plural. All but one are correct.
All but one?
Watch that.
Hey. Okay. We have 7 who answered again, which is all we had, or 8. I mean, so we'll go with that. Now, in answering this, don't give anything away, Max.
I'm just kidding.
In answering this, what direction does the electric field point?
Points towards the negative.
Okay, out of positive into negative. So the electric field between the parallel plates is like this. And if it's a negative charge,
It's going to flow.
it's going to go toward higher charge, which is higher voltage. And so it's going to go that way. Okay, so we did better understanding.
No, I didn't.
I just misunderstood.
You couldn't have both been wrong because only one person was wrong.
Well, I know she was wrong, but I misunderstood and got it right.
Do you have a question, Claudia?
So like, this is because technically the positive voltage has.
The positive voltage has a higher potential.
Higher potential energy.
But
So it's gonna
no, higher potential.
Higher potential.
Which for an electron translates to it's a lower potential energy situation. For a proton, it would be just the opposite.
Why did we really do this?
Well, okay, there is a really good balance. Let's say you go to medical school. Right. If you're in medical school, you're going to be studying things like how nerves conduct,
Right.
how the heart works. This is the basis of how all of that works.
I guess. But like,
What happened?
that just makes so much more sense.
Thanks to the antibiotics.
Okay, so it's a lower potential energy. The electron's gonna move where the lower potential energy.
That is correct,
Okay,
which is higher electric potential for an electron because of its negative charge.
so if it's gonna be lower potential energy, it will always be higher, like whatever you said.
For a negative charge. For a positive charge, it's reversed because change in potential energy
Yes.
is equal to Q delta V.
Can we
So-
write this down like real quick? We'll be like a table. So for a positive charge versus for a negative charge. That would be helpful.
What's the positive negative?
A positive is
Because it's
a
different.
proton, right?
Yeah.
Yeah.
Okay.
Also lower voltage. Makes sense.
Proton versus electron.
I know it's not much of a table, but it's the only table we can make here.
So this is helpful.
Or both of them. Come on, put an O there.
And then another section of it should be, because that's just the voltage, but that's different potential energy.
So I wrote that across the bottom because they both go to lower potential energy.
Oh, okay. Excellent, thank you.
All right. You are welcome. Electric fields. I already just showed this on the preceding slide, but electric fields, because they go out of positive and into negative, and for a point charge, positive charge means higher electric potential, negative charge means lower electric potential, then electric field lines always point in the direction of decreasing voltage, which, if we think about this logically, does make perfect sense, because the electric field line is pointing the direction that the force would be on a positive charge. And the positive charge is going to naturally go to lower potential energy, which means lower electric potential, which means electric field lines need to point in the direction of lower potential. All right, our last problem. A battery-powered lantern. Oh, I never talked about the electron volt, and I said I would. This is a symbol or a unit of convenience. We have potential energy change is equal to Q delta V. So, and that's the key to the next problem. If I have one electron goes through 2,000 volts change in electric potential. What's its change in energy? So it goes up 2,000 volts. If I want to know its change in energy, I'm going to say, oh, well, that's plus 2,000 volts multiplied by the charge of an electron. So I would calculate this as minus E times 2,000 volts. And instead of, well, what you would normally put is that's minus 1.602 times 10 to the minus 19 coulombs multiplied by 2,000. A volt is a joule per coulomb. And you'd get 3.204 times 10 to the minus 16 joules. But we physicists, I've told you before, we're lazy, right? We write this as, oh, that's a minus sign there, minus 2,000 electron charges times a volt. That was much simpler math, right? And so what is an EV? An EV is equal to the charge of an electron multiplied by a volt. Charge of electron 1.602 times 10 to the minus 19 coulombs. Hence 1 electron volt. Okay, it's okay. So 1 electron volt is equal to 1.602 times 10 to the minus 19 coulombs multiplied by 1 joule per coulomb, or 1.602 times 10 to the minus 19 joules. So an electron volt makes calculations a lot simpler if you're dealing with 1, 2, 3 electron charges. If you're dealing with large charges, such as that last problem, which obviously now we're not going to get to, then it's not going to help you out. But that's what the electron volt is. So that's why when that problem asks for the energy in electron volts, if it was dealing with an electron or a proton going through a certain voltage difference, it's much easier to do it in electron volts. You don't have to think. Okay, we got 2 minutes. It's the perfect time to go back and do it. So we go back to, that was number, okay. How much work is done by the electric force during the motion of the proton? Well, part B is in electron volts. And so for part B, we had a proton. Change back to drawing tool. We had a proton, and so we're going to have change in potential energy is equal to charge of a proton plus E multiplied by the voltage difference. In my case, that'd be 165 volts minus 43 volts. 165 minus 43, that's 122. So it's 122 electron volts. That's part B.
Yeah.
And then part C, part C, how much work is done by the electric force during the motion of the proton or the joule? Well, the work is minus the change in potential energy. And so we're going to have work equals minus change in potential energy equals minus 122 electron volts, and then I need to multiply it by 1.602 times 10 to the minus 19 coulombs per electron, and that gives me the answer in joules.
Wait, what?
Electron volts. What the negative?
Because this negative right here, because that's the definition of change of potential energy, is minus the work. All right, we're out of time. Have a happy Sabbath. And we're now, what, 1/8 of the way through the semester. In all things, praise